I appreciate it. I think people are going to be showing up a little later because of the weather. I got about time. Okay. All right, so my name is Mike Baginski. I'm a professor here, and I'll be teaching this random and signals and systems. I'm not sure what book you used before, if you're taking this for a second, but we're using this book. Now, Dr. Bashir chose this just for the summer. I think he's going to make a selection for Chan in the fall. Just wanted to tell you a heads up. I'll try to post a link of the PDF of Chan. A lot of these books, you're going to find that random signals and systems, and this is my opinion, is probably the most difficult abstract course as an undergrad. If it's taught right, it's a difficult course. Typically, when I had it, I think I had this. It was Larson and Schubert, but it was a junior-senior type course, and probably 30% failed the first time. It was very difficult. Signals and systems is a challenge, but if it's done right. But this course is very important also. So it's not only difficult, but it's extremely important, because most of the things you're doing in the real world are going to be things that are probabilistic in nature. The probability of things working right or not working right, and your profit and all that other stuff is based on that. Now, I'll tell you the other thing. The secret I found to most things, when they're difficult, is in the way, if I was in your shoes, this is what I did, because this is exactly what I did, and I did very well in the courses. I did every single problem available. I spent a lot of time, 2-3 hours sometimes, just at a crack, and maybe sometimes 5-10 hours if it's going to be before a quiz on like. I was going to wait for a second to get into how the course is going to operate, but that's the only way. I'll provide you with homework problems and solutions. I suggest, if you're serious about passing, because in the summer there's all sorts of thoughts about summertime. It's easier. I'll be an easier professor than Bashir. All this other stuff. It's more difficult. I want to tell you this. I don't like to say these kind of things because I like the summer too, but it's a compressed time frame. You're taking less courses, but this course itself will require more than 10 weeks because it's in a compressed time frame. And I don't make any bones about the fact you're going to need to work. If you try skating this course, you will fail. And this is the one course that I've taught before, and I've looked back at all the courses I've ever taught. This is the course I think you can go and just fall off the cliff in no time if you don't keep up with it. Now, if you've had this before, I've been told that there are people in here that have dropped or failed at least once. If you've had it before, I'm going to encourage you, please give yourself at least 2 hours to do the problems, and I'll try to be as straight with you guys as possible. So I guess this is the group we're going to be dealing with today, because I give you about 4 or 5 minutes extra. So what I do is, now how many have had me before? There's a lot of familiar faces. You've had me? If you've had me before, you can look around, you can talk to these people, they'll tell you. What I generally do is give quizzes every Friday, typically, and that's my standard thing. Did everybody get the OneNote link? You didn't.
Wait, what's it on?
It's on email.
It's on email. Oh, I'll look at it. I didn't have it.
I don't use Canvas. I've had problems with Canvas. I try to post the grades in Canvas. I've had nothing but trouble with them, because if you try to do anything where a grade adjustment or scaling on Canvas, it'll show 2 different grades, and I can't just get rid of one easily, put it to you that way. So I'm going to use OneNote. I'll try to make your grades available on Canvas as best I can. Quizzes every Friday. If you look at that, 35% of your grade is made up of your quiz average. So be aware of this, and don't just do the Thursday night cram. Here, in this course especially, it's bad with EMAG, but it's much worse here. This is a guaranteed way to fail. Just don't do it until Friday. You get confused as heck, especially with a lot of stuff, and then you take the quiz and you don't know what you're doing, and it gets worse and worse and worse. See, there's some very bright people that fail these courses if they don't keep up. Second thing I'll tell you is this. If you have questions, let me know. I always try to take questions at the beginning of class related to the previous homework, and I try to address them in a very direct way. I do not try to confuse you. I'm just trying to be as straight as I can. And the other thing about this, now this is kind of personal to me, I teach radar, and I'm learning Python and all this other stuff. I'm going to try to learn Python this, I mean, really for this course, because a lot of the exercises have, they're written in either Python or MATLAB. A lot of this stuff, I think Adele Bashir uses also. Python, do you all know what I'm talking about with Python? They have a language called R. I'm not going to mess with that. The only thing I'm going to do is either Python or MATLAB, probably Python more and more as it goes on, because of one thing, it's free. And it's everywhere. And I'm very interested in AI, and really neural nets, specifically for a lot of stuff that I do. Now, in radar, one of the biggest problems we have with that I have teaching radar is the students come in and they have fumbled around with random signals and systems, They don't know a lot about Laplace transform, Fourier transform, signal analysis, Fourier series. I mean, they kind of have an idea, but they're very, come in and they have very little understanding of the reason O'Reilly distribution for a lot of things are so much more effective in determining probabilistic type of information, like the probability of a target being there or not, versus the Gaussian. You all know what I'm talking about with Gaussian profiles? I mean, I think don't you get that in math and physics? Don't they talk about this or not? I don't know. I mean, Gaussian or what? They're natural events where you have, it's called a Gaussian curve, it's a bell curve, and it just talks about the probabilistic nature. It's a probability density function of an event being between typically minus infinity and plus infinity if it has a zero mean. And you can figure out the probability by integrating that probability density function over the range that you want the probability of the event occurring. Now I'm saying this, well, that's all nice, well, and all that stuff, but negative values with radar analysis are horrible. So Rayleigh distribution is an absolute value of some kind of random variable. We'll get into these things. Have you heard of Rayleigh distributions?
No.
Have you heard of Gaussian?
Yes.
Okay. You're going to see all this stuff, and the reason it's important. Now, if you're, I don't know this class what your interests are and stuff like this, but I'll just throw this pitch out, and I do it every time. If you can, if I was sitting where you are, I would make it a single point to learn artificial intelligence. I would really learn neural nets, and I would learn Python, because everybody, and you see ChatGPT, that's only the drop in the bucket of what's going on now. My brothers up at Dynetics, they're using that for everything, and I mean everything in their book. They're designing with it, analyzing with it, they're writing documents with it. They have their own premium brand. Basically, it's just for the company. It's not for public use. It's a type of AI thing. But those things are so so valuable to you. When I came through years ago, there was something called a genetic algorithm in the early 90s. All right, you can take a derivative or a gradient. You can set it equal to 0. Find the point where it's either a min or max, and evaluate it and find out. That is mathematically something you do. It's very easy to do, and it's easy to understand. When you have something that has a whole lot of minimums or maximums, something that's fluctuating in a random way, but you have a definition of that surface function, you want to find where the absolute minimum is. Well, some of these things have an infinite amount of absolute minimums. So you can do it with a gradient descent methods and things like this, but you're going to run out of time because it would take forever. Genetic algorithms allow you, in a very clever way, to get to it's probabilistically the minimum or the maximum, but it does it in a very clever way, and it will find, and I was shocked how well these things work. So I got real interested in that. Now remember, this is not AI. AI is a lot different because it uses, basically it's based on how the brain works. The brain has neurons. Have you had AI yet? Have you had neural nets or anything? God, please take a course in it. You would thank me 100 times over when you graduate. It's where everybody seems to be interested. So what it's doing is teaching, like how come you can look at, say, that and know it's a fire or some sort of a red box that has a fire alarm. You looked at, right? Try to train any kind of robotic device to do that. It's nearly impossible, right? Because your brain is a neural net and you've been being taught since the time you were young how to identify things. In your mind,
I mean, you don't transmit any kind of information. A bat at least transmits sonar and gets reflected things and does the process. But there's all this ambient light and stuff like this. Well, with radar, for instance, passive radar is something where there's so much microwave energy and everything out there. Why transmit? Just use the background radiation, the reflective values, just like we do with our eyes, and identify everything in the fields that you're interested in. That's sort of a thing. This gets really deep here quick, but the only way you can do these type of problems is by teaching things how to think and learn. And that's AI in a nutshell, so I'm just throwing that out there because probabilistic approach with AI is going to change. Have you all used ChatGPT at all? Or something like it? It's powerful. I mean, I don't care who you are. I was shocked at how well it did stuff because it'll go ahead and it'll just peruse the internet, find stuff, and tell a story. That would basically solve problems. I'm not lying about this. I tried that and I was shocked. It got the wrong answer several times in my radar class, but it did solve everything. Now I see where these kids are getting these things. Don't use it for solving problems in general. You're going to find some really wacko answers. But it is, maybe it's getting better because it's a learning algorithm. So I'd recommend you take that. Now for this particular course, I think we've got the full complement of students today. We've got 2, 4, 6, 8, 9. We're supposedly got 10 or 12. Who?
I think we're missing Luke. He's supposed to be in this class.
Okay, there may be more. So what I do is you get Friday quizzes. You're going to get one midterm. It's worth 25%. One final worth 35%. And if you look, I believe on there, that's the way it goes. But you can check me on that, right? And is that right, 25 or 30? The first test is either 25 or 30, I forgot. And then there's going to be a midterm. The final is weighted the heaviest. But the quiz grades are heavyweight now. So don't get in the habit. Just, well, I'm going to the beach. You got to be focused on this. This is only, it's a short course. In my opinion, this material, the amount we're covering, is substantial and it's abstract. All right, that's my pitch there. Second thing I want to tell you is this is the book, and I didn't select this at Al Bashir. It's a good book, but it's written it is more written from a mathematical perspective than an electrical engineering perspective, if you know what I mean. It's general. The ideas and concepts apply to everything. But rolling dice is not something in electrical engineering that you teach. We don't talk about that. We talk about resistors and circuits and gain and all that stuff. But this book tries to show the concepts generally and help you. You haven't missed much. And do you all have how many have a copy of this book?
Only it.
All right. What I suggest is you get a copy of this book as soon as possible. Now the tests and quizzes are closed book, closed notes. You get to use your calculators. If you've had me, anytime, if you have any questions and I'm not available, just ask the people who've had me. You just got here. Have you had me before? Okay, then you know the deal. All right. The quizzes are based on the homework. Please keep up with the homework. So that said, now we're going to. How many have this book? You do. Do you have Cooper and Millen, the old one? Which book do you have? I mean, sorry, maybe you don't have any. If you haven't got it, you could probably pick these things up online. I don't know how much they are. Now, it's just me. Anymore, I'm wondering if I should say this. When I was a student, what I did is any book in engineering or physics or math that I used a lot, I kept and I wrote in it. I made all sorts of notations that you can come upstairs and see. I have old circuits books from Hayden Kimmel. I have EMAG books from Harrington and all. I mean, they're sort of the legends, some of these people. And I've written all over them because that's the one thing I won't lose. I'll lose notes and stuff, but I don't lose books generally. They might get stolen, but I don't lose them. And books, you'll find out that you don't know how to do it, but a long time ago you did. You know where it is. I don't know if you've ever found this to be true in physics or in your math, especially with math, the wild mathematics that has to do with some of the stuff, there's Gradstein and Rivers, a book about that thing. Does anybody know what I'm talking about? Oh, God. Well, if you've ever had, if some of you go to grad school and you see what I'm talking about, some of the things that you have to do, you have to go through the analytic solutions of a lot of crazy stuff. The del squared equation, say the Helmholtz equation, and spherical coordinates with certain constraints, or polar spherical. Man, some of that stuff's really hairy. So you did it once, you know where it is, you can go back and find how you did it, even though you don't remember all the details at this moment in time. You need it for something. Anyway, that said, with this book, I looked through it. If you get this, and I have, I'm going to just tell you, the first chapter, I read through it is straightforward. There's nothing here that's tricky. So I'm going to go ahead and start talking about this. And I don't make PowerPoints, but I may show some just because I think it'll make some of this stuff a little more clear. But we're going to go ahead and talk about this. So with probability, what are we really talking about? Outcomes aren't certain. They're not deterministic, not guaranteed one way or the other. They are based on a chance or a likelihood of an event. The best thing is dice. Think about probability. So here's where I'm going to start. Dice have, if it's one die and it's thrown and it's called a fair dice, the probability of any number on that cube is exactly 1/6. There are 6 values, right? So the probability of anything, if you have dice, or just one die, I guess. All right. You have outcomes of possible 1, 2, 3, 4, 5, and 6. Those, you don't have 0. You all with me, class? That's their 6 faces. That's the possible outcomes. If it's a fair dice, the probability of each one of those outcomes is the same. Now, if we're talking about just one dice and a roll, then there's a thing, a set, and the set would be composed of all these values. 1, 2, 3, 4, 5, 6. Have you heard of the term sets before?
Yes.
All right, that's just identifying all members of this particular group that we're going to be talking about. We're going to assume it's a fair dice, all right? So if I say that A is going to be equal to 1, 3, and 6, and I say that B, these are sets as well, B is equal to 2, 4, and 5, okay? One way of representing what I've just written is with something called a Venn diagram. Have you heard of Venn diagrams? Now, did anybody here take logic? Or
I took discrete math.
well, then you've heard of them, all right? But if you took, the first time I had this was, I took a course in philosophy called logic, but the guy was actually doing all the stuff that's based on reasoning and math, which was nice. So a Venn diagram is this. Basically this. I'm going to say that A represents those values. Are there any values in common?
No.
All right, that means they have no members in common like that, okay? They are independent. One set of values is not dependent on the others, or it is no way influencing this. So if you look at this, and this would be something called a set. Now the set has all members. If I look at this, I have 1, 2, 3, 4, 5, 6. So every single member is shown just between A and B, but they have no members shown between each other, or that are in common. You all with me? So the set is just A and B. I'm trying to really, you wouldn't even have that set there. You just have A and B, and the set would be the entirety of A and B. Now, if you look at this, there are symbols we use to talk about, and since you've had this, you're going to hear some different terms. There are sometimes they call complement, and sometimes they call it, I mean, this is from De Morgan's theory, they'll just put a bar over it. All right. But if I take a look at this, if this is A, then A bar, And this is, or, now Bashir's, if you had Bashir's, he uses the complement symbol, didn't he? Anybody have him before? Or see it still?
He used a bar.
What's that?
He used a bar.
He did.
Or like a prime.
Oh, he used the prime here, like that?
Yep.
All right, typically it's a bar or a C, a complement. Now, the bar means everything in the set but A. That's all it means. You've seen this before. Remember, you do have gates. You've had NOR gates, you've had OR gates, you've had AND gates, you've had NOT gates. All the things I'm showing you, you'll see directly work into Boolean algebra and logic. I mean, you can implement all the stuff that I'm showing you with gates in terms of the math later. Y'all had Carnot mapping, haven't you?
K-Man.
Yeah.
Yeah.
Okay, so what is A bar? Just tell me. Take one look. If all the values are 1 through 6, and that's A, what is A bar? Everything that ain't. Or B. Follow me? So this is really, I just put it B. That's it. I'm trying to make it as simple as possible. Okay? Now, if it's a fair dice, I'm going to ask something that's not directly related to this, but see how you're feeling today, how you're reasoning. If I just ask you the probability of getting 1, 3, or 5, I want the probability of either a 1, a 3, or 5 happening with an even die. What would it be? I mean, a 1 coming up, a 3 coming up, or a 5?
50%.
How did you get that? You're right. Your instincts are right.
Half of the total set.
You simply get a ratio of what?
3/6.
And or the areas, if you think the area was proportional to numbers in the sets. Now, that's one of the reasons we do Venn diagrams, because they give your mind an image to think about when you think about probability, and I'll get to that. The probability of A occurring, given that B happened last time or anything like that, it's independent, it doesn't matter. You all follow me on this one? And you're going to see more about this, but if I look at this, what it would be is the probability of a 1 is 1/6, the probability of a 3 is 1/6, and the probability of a 5 right here is 1/6, so it's 3/6, right? You're just taking a look at the probability of each event, the possibility, and you're adding them up, right? Okay? I'm trying to make this as simple as possible. There's formal ways to do this, but I think it's a lot easier. All right, now, this is the simplest thing I can think of. Now I'm gonna go ahead and do the next. We're gonna still use this example, or this dice rolling, but remember the bar or the C just means everything but that. And in his book, you'll have some stuff. Most of the time, when I was learning probabilistic stuff, statistics and all the higher order stuff, I always thought in terms of areas. I mean, it's a natural thing to do. So if I look at this as the total set, we're talking about dice outcomes here. Now I'm going to define A as simply 1 and 2, and I'm going to define B right here as 2, 3, and 4. Okay.
Would you mind going back? You said in terms of what? And you said you like to think of it in terms of
Areas.
areas.
And what I'm talking about is I'm trying to show proportionality, like A being in some ways proportional to number of members shown in A, the set A, or the group A, and then B being proportional. So if the total, it'll help you, it really will. So if I have this, these are two things, and I'm going to draw a Venn diagram to represent that. Here's my set of all values, S, and that's 1 through 6. A has 1 and 2. Here's A. And then B has 2, 3, and 4. Now, you all with me, class? And the reason there's overlap is because they have a common member, too. So if I think about this, now we're going to talk about different symbols. And in the book, I'll tell you where these things are. We're going to talk about union, intersection, and we'll talk about complements. So if you look, you might as well just write this down, and I may put a PowerPoint up here just because it'll help some of you see things. And he's going to show this stuff on page 4 and 5 with Venn diagrams, and he'll give you and he does use the word union and intersection for some of the things. So if I looked at A union B, now that U just means union. It means everything in A and B. Doesn't matter if there's overlap. Y'all with me, class? So it's everything. So what is that? Well, it's not quite everything possible. Y'all see that? But it's quite a lot. It would be 1, 2, 3, and 4. Now, if you look at this and you're talking about the union, or if you wanted to represent what I'm talking about visually, you would say everything there would be the union. It would represent the union. Does that make sense then? There's nothing tricky about that. If I say this, and maybe I'll use this blue. If I say A and the symbol is intersection of B, so that means it has to have members of both, the members in this set have to be available in both A and B. Y'all with me? Have you seen this symbol before? In what class?
It was like back in my last when I was taking math.
Oh wait, you're a math student. I'm talking about engineering or physics in your math courses here. Because I think, don't they use this with Carnot mapping and stuff? Don't they use these symbols? They didn't use
It came up? No, it came up.
We use these kind of things for, we shape, like, I don't want to go too far. So what is this? What are the ones that are in common with both? There's only one, two. Okay. So what would this be? Now think about it.
Real quick, was that A inclusive B? Is that how you say it, or what is that? Intersecting.
I mean, the term is intersection. There are other terms that I've heard used, and if you've had a math course, you may have some different, because it depends sometimes on the application. In engineering, a lot of times they use complement. They don't use bar. I mean, that's how I always heard it. There's going to be other terms, but the symbols are always the same in the intent or the meaning. So what is this? Just everything that isn't what? Above, right? So what is it? 1, 3, 4, 5, 6, because it's the set has everything, right? Y'all with me, class? You remember this stuff? I mean, something like this had to be in your, you can't build any of these flip-flop things where you have adders and subtractors without this kind of reason. It's binary reason. Okay. Now, if I look at this right here, where does that actually symbolically occur? It's right here. That would be a visual representation of A intersect B. Make sense to everybody? Making it real simple. And he goes through more examples. Now, something else I got to tell you about probability. If we're talking about, still talking about one die rolling it, these are the possible outcomes, right? So the probability of if you might say, if the dice is rolled, the probability of 1, 2, 3, 4, 5, 6 occurring has to be 1. Y'all with me? We talk about the greatest the probability can be is 1, which is 100%. And the minimal is 0, but it can never be negative. You with me in this class? And this is just something, you will see people come up with negative values for the probability of something. See, that's like negative mass, all right? Physicists use that idea, but there is no such thing as negative mass. Just isn't. At least, didn't used to, but anymore. So if I take a look at this, all right, just based on what I'm talking about here, you know that this is just giving you, it doesn't show you a whole lot, but it's giving you some visual tools to work with. So when we talk about probability of something, and this is something I'm going to say now, because I'm trying to show you the kind of areal relationship, you know the probability of A intersect B, just because the area is much less, is less than the probability of A or the probability of B. I hope you can follow me on this, right? You know that there's also something called conditional probability, and I'm only using two subsets, A and B. In the book, he's going to have 4, 5, 6, 7. But there's something else that you have to understand. Because of the the ratio of areas that I think helps is this. When you take a look at, here's the set, and if this is A, and this is B, and this right here would be A intersect B right there. I want you to just follow me on this. If I take a look at this for a second, I can rationally, and this is the total set of all values, and I'm just leaving it as 1 through 6 as possible outcomes. If you take a look at this, and I wanted to get, I have not really gone down this route, but what is the probability of A occurring given B occurred? This is the symbol for that. So what it's saying, B occurred, and what is the probability of A occurring? Now, remember I talked to you about areas? And I made sure I made it a fair diet. Take a look just for a second. All right. Let me erase this. I'm going a little further out on this one, but I think it'll help you understand. So I want the probability of A occurring. Here's A, right? Giving B occurred. So it says this has happened. So really, the only place where B would overlap A is right here, right? Can you all see that? Now, this is a fair dice. So how would you do that? Think about it intuitively. I told you that B occurred. That's down here. That's B. This happened. You don't know what value, but you know this occurred. Either 2, 3, or 4 occurred. Follow me? One of those values. So what's the probability that this occurred? Can you see it's a ratio of areas? So this has what? 3 possible values, right? The only value that intersects is the 2. 1 value, so it would be 1 into 3 is 1/3. Now I'm going a little further on this one because it's a fair dice. Does that make sense to everybody? Okay. Y'all with me? I'm talking about these are the outcomes, right? Possible outcomes. Yeah. It's probabilistic. Does everybody follow me on this one? I don't know how Bashir explained this. I try to, if you've had him or had anybody for these kind of courses, I try to make this super simple. Well, in the book does it, he's going to show not just A and B, he'll have A, B, C, D, and some overlap, some not. He'll be talking about all different manner of defining different areas. I'm trying to show you the relationship of probability, if it's a fair dice. If it isn't a fair dice, it's different, completely different. But we're making it simple for them. So that is something that you'll see that way of doing business, but I'm trying to make it easy. All right, now, in the book, I'm going to just say this. There's things called De Morgan's laws, and it'll do things like this. He has all sorts of ways of saying what, another way of saying something easy. So if I look at this, if I have this right here, A intersect B, and I'm trying to give you the visual there. What is A intersect B bar? Just think about it. Every value that isn't in that space, that's the dark shaded space in the center, right? The dark space in the center has one value too, right? Does that make sense? Everything that isn't is up here minus the 2. That's what I'm trying to show you. Well, so this is really going to be, and he'll show this so many different ways. If you write this down, I really don't. This is on page 4, but it's really going to A bar union. So this is really going to be A bar union B bar. Now, just think about this for a second. According to this, if you think about what I just put there, these are just proofs, but you'll understand why I'm mentioning this now. And let me do this again. So here's A, and here's B. Now, work with me on this so you can see. This is one of De Morgan's proofs, but you can get this just by looking. If I take a look at this, what is A bar? Well, A bar, I'll try to draw it out. It's everything that is in A. So it's everything that is in A. Makes sense? It's everything out there, right? What is B bar? Well, it's everything that's not B. And I hope you can see that, right? Now, I just said that this has one, let me just put one thing down. I know that this value is 2, right? We've already defined that. Do you remember that? Oh, sorry. The A intersect B is 2. Everything but that is going to be the values 1, 3, 4, 5, and 6. That's right. That's with me because A intersect B has one value. The bar over means everything but that. It's all the other values. If you look at this, and I'm just work with me. I mean, because that means that's there and that's there as well. Everything that I'm showing you there, except this little portion, would be included. And that's exactly what we got. That's one of De Morgan's laws. There's tons of these little things, but usually you don't need to mess with those because you can see. Go ahead.
So in A of 1 and 2, B of 2, 3, 4, so 5 and 6, since they don't exist in A or B, it's in that square called set.
Yes.
Is that why you scraped
Yeah.
scratched all
And
over?
it's just a visual representation. It helps you, honestly, it'll help you in the long run once you see it. He doesn't even really talk about the probabilities in this chapter, the first chapter much. He does a little bit, but you're going to see that if you understand how to represent the areas, you'll be much better off understanding that and then getting, all the different probabilities. Now, he'll have not just A and B, he'll have A, B, and C, and D, and show you all sorts of stuff. Sets are independent, this is just a term, if A and B have no members in common. If they have members in common, then one is dependent on the other set's values. That's the simple way to think about it. Okay. All right, so I think I've touched all the basic stuff here. He has, he does a lot of mathematical, just to prove things that are, in my opinion, kind of obvious. So if I take a look at this, work with me. What is A union A bar? Everything, right? Everything that's not A and A better make up all possible outcomes, so we're not talking about probability. that's all, and he will say, well, that's everything, that is the definition of a set. There's nothing really new there. I mean, that's the reason. And if I said A, and there's a thing called a null set that has no members. So I don't want to spend too much time on this, but if there's no members at all, it's called a null set, or zero. You'll have zero. So if I have A, and I have A union with a null set, or with zero, that's what he'll have. It's just A, okay? Now, there's proofs on this. This is not necessary. I think we got this just by thinking for a second. And there's more of these things in this first chapter that I see. And he will, oh my gosh. I'm looking, I got notes, plenty of things that I could talk about, but I think you guys see a lot of this. Now, I'm trying to say, trying to make this somewhat obvious, but not too obvious. So things are independent if one doesn't depend on the other one occurring or not occurring.
Real quick, just going back on that. So A intersect A bar, would that be like does not exist because you can't
Hold it, you're saying
A intersect A bar?
about,
Is that like does not exist?
that's zero.
Is-
That is the null set.
Got you.
That's the null set. Yeah, I mean, but he talks about these things. Most of that, it'll just be, well, this is intuitive, you know. But there's reasons he does this, and it comes later. You don't see it now, but it comes later, because you're gonna see there's some tricks. I'm gonna show you one trick right now. He does talk about, in here, by the way, I think this book does a fair job making it easy to understand. This is not something that's just steeped in some mathematical theory that makes it real, I guess, it's not apparent, it's pretty apparent and stuff. So when you're talking about things that are independent, the way to draw it is that A and B have nothing in common. That's the way to symbolize it. And the probability of A times B is really probability of A plus the probability of B. But it's better I show you some of these things operationally. Now, there's one thing and this is something that does apply to engineering, so I want you to follow me on this one, especially to telecommunications and wireless. Anybody here in wireless or telecommunications work? If you are, you know that the link you'll be very aware of. And so let me give you a page number for this, and then I want to show you go about business here, and I'll show you the tricks that he really doesn't show you. So this starts on page 18 of the book, if you write it down. And it's a simple 3-link problem, and I'm going to show you some. There's a lot of tricks to these things. And I say tricks, it's more or less just reasoning it out correctly. You don't have to write down every possible outcome. I'm going to show you some stuff. I'm being a little casual here, but this is on page 18 again. So here's something where you got he uses the word source and destination. So over here, I'm going to say I have some source. I'm going to keep this as simple as possible. It can get much more complicated very quickly, but I want you to just follow me on this, and I think it'll help. This is the destination. Now, we're going to have a route, a signal route, that can go like this. And there's a probability of this link, and I'll call it link 1, being operational, and this probability will be P. I'm going to leave the probabilities all be P for this, all right, for the same. Make sense to everybody? So if I said, what's the probability of this link working? It would be P. What's the probability of the link not working? 1 minus P. Make sense to everybody? All right, now I'm going to add something. I want you to watch this. I'm I'm gonna say, now I'm gonna have a link 2 and link 3. This, you can think of this as just a repeater point. So the signal has to go from here to here. Now, each one of these we're going to say has a probability of P working. I want to keep them all the same to make it easy to ration it. Right? Y'all follow me in this? How many of you seen these kind of problems? They're very common in telecommunications, aren't they? So how do you do that? Well, first of all, the mistake is you try to write one equation just on all that. And you could say, if you look at every possibility, and this is the way he does it, and it's stupid. He'll say link 1, link 2, link 3, and this is standard Boolean stuff. All right, a 1 represent it's working, a 0 represent it doesn't. So you could have 0, 0, 0, nothing works, and there would be no communication. Y'all with me? Then you could have 0, 0, 1. And, well, that's L3. If L3 works, but the other two don't work, there's no communication. Y'all follow? This has to work and this for communication to go this way. This has to work for that way. And either one working would be a success. Y'all with me? If this network worked, this. Did you have a question?
So this is kind of like how the internet, where there's redundancy, if I.
Yeah, but this, before we go down that road, just listen to me. And you'll see the reasoning and the trick. And we could keep going down. Then you can have 0, 1, 0. This is binary counting, right? We have 8 values. We could go figure the success rates. We have 8 possibilities, right? And we could see how many of the successes out of that, right? All right, now, here's the way you do it. Before you go down that route. That's the bad way to do it. If you've had it, if you've gone through anything like this, and because this is a real simple one, you can make these things hugely complicated. If you're doing it that way, you're killing yourself. Let me show you. The trick is, always make it as simple as possible. Let's start with this link here. If I just have link 2 and link 3 here, this has a probability of working P, this has a probability of P of working, right? For that to work, that length, both of those have to work. For both of those to work, the probability would be P squared, because they're independent. Y'all follow me in this one, class? As you read through the chapter, you see them say, so this entire link can be replaced by a single link, right? I'll call it L23, that has a probability of success of P squared. Make sense to everybody? Y'all agree? If they're independent, then the only possible way, and they are, all right? I don't want to ever even think about doing dependency with something like this, because it would really get confusing. But y'all follow the rationale? So what I can do here is say, I'll replace this link by just one link, those two. He doesn't do it this way. Wish you would, because that's the way to do it. Did you read this? Did you read this chapter or not?
I mean, I had like this type of problem with Bashir. So,
Did he teach it this way?
yeah.
Okay, good. Because I looked in the book, they didn't show this, which irritated me. I mean, in this book. So I can replace this one with a single link that just is this. Right? And they're in parallel. And this is going to be L23, and this has P squared, right? Now follow me on this. If I think about this for a second, there's what? There's 4 possibilities if you think about this. This link can't work, this link can't work. This link can work, which is good, and this link not working. This link doesn't work, but this link works, or they both work, right? The only one I'm really interested in is the one where both don't work. Because if they both don't work, it doesn't work, right? But if either one works. So now, instead of thinking about working, now I say this not working would be 1 minus P. I don't know how they taught this in some of the other courses, but usually something like this is you've been exposed to at least once. What about this one up here? Well, this one would be 1 minus p squared. So this is the probability of it not working. Make sense? And this is the probability of it not working, right? Y'all with me? In order for this thing not to work, both of these have to happen, and they are independent. You all with me? So that means the probability of link not working would be 1 minus p squared times 1 minus p. Now that would be the probability of it not working, right? So what's the probability of it working? 1 minus that, right? Just think about it. If it's not making sense to you, this would be the probability of it working. So this right here, probability of link, or really of, yeah, I'll use link, working. Now we can go ahead and expand this. So I have 1 minus, and it's going to be 1 minus p squared times 1 minus p. And I got to expand this. So it's 1 minus, so the first two minus 1, and then minus p squared plus p squared plus p, and then it's going to be minus p cubed. So that means the ones go, and I have p plus p squared minus p cubed is, if they're the same, that we're assuming that the probability of each one of these links working is the same. This is on page, by the way, 18 in the book. And if you look at the top of page 19, and this is, he has this in equation 1.8, and p plus p squared minus p cubed. Now, I did this, it's a simple one, but you should see now the benefit of using what? The complement, or instead of using the probability of success, and just looking at that, I'm using the probability of failure, and once I know the probability of failure, subtract that from 1, I get the probability of communicating successfully. But you'll notice I didn't go through this, all this stuff. You follow me on this, class? He does mention some of this stuff, how to do it correctly, but I looked at that and I didn't see what I was hoping to see. This, because he has that, the possible outcomes table on page 18. So then he goes into a much more complicated, in my opinion, an example, but I'll just tell you this, and I'm going to ask you before I go ahead and do it. You all see that with parallel things, you want to find the possibility of it not working, right? With series things, the possibility of it working, and you keep reducing the complexity. So I'm going to ask you this now. This class goes to 11, right?
Yes.
I'm not trying to waste time here, but I think I can help you. I do have some PowerPoint slides. I really don't like to use them unless I have to, things like this, because I don't think they help. This is fairly straightforward and simple, but here's how it gets complicated. And this is a type of problem on a test. If you don't know the correct procedure, you'll just get lost in the shuffle. You won't be able to get all the outcomes correct. All right, suppose I have this. Here's my source. Here's my destination. And in his book, he's going to have 6 links. So he's going to have a link like this, but it gets more complicated. I'll call this L1, L2. He'll have a direct path here, L3. Then he'll have something like this, L4, L5, L6. You with me? Each one of these will have a different possibly different probability of working. Can you all follow me on this? So now, I want to figure out the probability of the link working. Meaning, we're engineers, if they're in parallel, either one in parallel working is a success, right? If they're in series, both of them have to be working for the thing to work. That's the idea behind this. And this is, by the way, a standard communication kind of link problem, whether you know it or not, but it's usually, they get much more complicated than this because the probabilities can be a function of time, and they also can be a function of the state of other points in the circuit. So it's kind of crazy. So if all these have different probabilities, this would be of success, P1, P2, P3, these are success, P4, P5, and P6. How would you go about finding the probability of the link working? Well, you don't start and write down every possibility. Y'all with me on this class? The probabilities are different, but what can you do right off the bat?
You can simplify the ones in series and then.
Follow me? Everybody see this? Let's simplify this one. What do I do?
P squared?
They're different. P1 times P2. With me?
Okay.
You're right about that. Just work with me, guys. So this one becomes P1, P2, right? What about this one? Just leave it at P3, right? I'm gonna get rid of it. What about this one?
P4, P5, P6.
Pain, right? So this one becomes, they're all parallel. P4, P5, P6, all right? Now, this is the catch-all. How do you go about calculating the probability it's working?
The 1 minus,
We find out the probability it failed.
yeah,
All right, so what's the probability that this one fails?
1 minus P1, P2.
Y'all follow me on this, guys? What about this one?
1 minus P3.
And that's failure, right? Make sure, failure, right? What about this one?
1 minus P4, P5, P6.
All right, give everybody a second to think. Depending on how much coffee you had, or sleep, or both, is how fast you'll see certain things. Now, don't get the answer. Now, how do I find out the probability? Now I know the failure of each one of these, but now what do I do with that? Go ahead.
1 minus times everything those together.
We know the probability of it not working would be the probability of this times this, because they are independent, times this. You with me? So the probability of a failure, this isn't as, I don't know if you did this way. 1 minus P1, P2. 1 minus, you can have fun squaring this or cubing it, P3. And then 1 minus P4, P5, P4, P5, P6, right? That's failure. 1 minus that is the probability of success. You all see it's a pain, but it's a whole lot easier. Yeah.
Is that like taking the inverse when you do the 1 minus on the outside of, when you multiply everything together, that's the
All
probability
these
of failure?
things, this right here is the probability of it not working.
Okay.
They all have to fail.
Yeah.
They all have to fail, right? The only way you have to multiply them together because the probability of each thing is independent. Can you all follow me on that? 1 minus, that's the probability of it's working. That's the way you think of these things. Now, here's the nice thing, just for a second. Typically, these numbers are easy. P1 is 1/2, 1/4, something like this, follow me? So if I have like P1 1/2, P2 1/4, that's 1/8. 1 minus that is 7/8. That's a nice number. You don't have to go and pound that thing out on the test. I would probably give you actual numbers on quizzes and stuff that would make your life a little more painless. Because some of these things, especially, I mean, these are relatively simple examples, but some of these complicated ones, the only way to do it is writing a script like a Python or MATLAB code, because they just get bizarre. Did that make sense to you?
Yeah.
Bashir probably showed that.
Yeah.
I mean, something like that, but he may have gotten really complicated. Yeah.
So,
Hold on for 1 second. Let me just say this. In his book, I just want you guys to see it. He does the whole table for that crazy one. Don't do that. I mean, that's the problem. You're gonna have people cramming and stuff like this. Oh, that's how they show. Don't do that. Don't do a lot of stuff you see online about this stuff. That's a very hard way to go through. He does break it down, how to reduce the complexity. Now, what were you gonna say?
So is the probability of failure like the inverse of probability of success?
Remember, the probability of a failure plus the probability of success has to be 1. That's the set idea. If it's not 1, we're not talking probability, we're talking about Disney or something. But it has to be something real. In other words, you can't talk about things that don't obey basic laws of probability. If you're talking about, you're throwing the dice, it's happening. There's only so many possibilities. The numbers 1 through 6 can come out. You can't get a -1, you can't get 12. You all with me? That's in the probability of something occurring is always positive. It can't be negative. It can be 0, but it can't be negative. And that's one of the things you'll see happening with, it's easy to make mathematical errors in codes. But when you get a probability it's negative, there's something really wrong with your code. Something that you may not see, but you gotta go back and make it right. I'll warn you about these things too. It's easy to fall on your face with this kind of stuff. Now I want to talk about just you're talking. Read me these problems. We're going to talk about, see if these things are legit or not. Probability. I'm going through this. To me, it's obvious, but it may be helpful. All right. If we just do the first problem, we're going to skip around. The reason I'm talking about this is he's trying to make you aware of the legitimacy of certain things happening. Things that are allowed and things that can never occur. And like what is and what should never be kind of thing. Because you're going to see, and you'll have this happen to you, where you're going to get outcomes that you got to just notice that can't be, or else you're going to keep going down the road and make a disaster. So this is the first problem, and he's asking legitimate probabilities. So what's the first one?
E to the negative p power.
And is p positive? Is p between 0
P
and
is
1?
between 0 and 1 positive.
Greater than, equal to 0, less than or equal to 1. Now, is that a legitimate probability? Now, just think what it has to be between 0 and 1, right? If p is between 0 and 1, is that between 0 and 1? Yes, right? If it's negative, right? E to the minus p. E to the 0 is 1. E to the minus 1 is just 1 over e. They're all positive. You all follow me? What's the next one? So yes.
E to the p.
Think. Is it legit or not, and why?
Only when
Do e to the 0 is 1. That's legit. What is e to the 1?
2.
2.7.
Bigger than 1? No. I'm just showing you. That's the reason. Go.
Cosine 2
All
pi
right.
p
Cosine 2 pi p.
is
All right. Class, think. Please. What does a cosine waveform look like? Right? If this is the argument of 2 pi p this way, what are these values? Negative. Are they allowed?
no.
No. That's not a legit. Follow me? Keep going.
P squared minus 2 pi plus 1.
Square minus 2p
Or 2p, my bad.
minus 1
Plus 1.
plus. All right, is that legit? How would you do it? P is now, probably we make a fun, this is what I do. Let's call this y, all right? Plot, what does it look like? Try p equals 0, what is it? If this is p. P equals 0, it's 1, right? P equal 1/2. You want to know how to do it? Take the derivative, set it equal to 0. All right? Follow me on this, guys? If you take the derivative of that, I mean, you don't know what that looks like. You kind of do, but what is your gut feel on this one? So take the derivative of that, set it equal to 0. What do you get?
2p minus 1.
dy dp equals 2p minus 2, right? Isn't that right? All right, now, that's the derivative. Where is it equal to 0?
1.
P equals 1. P equal 1, what's the value? 1 minus 2 plus is 0, right? Is fact, it is a legitimate probability. As a matter of fact, I've got, should let you, yeah, it is. Follow me? But that's the reason. Take a derivative if you want to figure out the max. Go ahead.
3p minus 2.
All right, this is a good one. I think. And do, where's the actual? I gotta get some spray for this thing to really work. Say it again.
3p minus 2.
All right. P, remember, greater than 0, less than 1, or equal to 1. So what is that value? Try it 1.
1 is 1,
All right, keep going. What if P equals 0?
-2.
Is that possible?
No.
No. Follow me? It's not. You got another one for me?
That was the last one.
All right, go to the next problem.
Assume, yeah,
Yeah,
it's the
very
same
easy.
thing. Pi of p, or square root p.
What, this is the next problem? Let's see if it's legit. Is that the question?
Yeah, it's asking the same thing between 0 and 1.
All right, so it's square root of P.
These are square root of p.
Is it? Yeah. Follow me?
Then, the next one is 1 over p.
1 over P. What do you think?
P is 0, it's undefined.
Can't be greater than 1, can it? Follow me? As it gets less than 1, that goes to a value, what, larger than 1, it's impossible. No. Is this helping you just go through this or not?
Yeah.
Go ahead.
P minus 1, and it's all cubed.
All right, call that Y. Now, think about it. What does that look like? P can be between 0 and 1. Notice the cubing, right? Start with 0. When P equals 0, I have -1 cubed, which is,
Minus 1.
is that allowed?
No.
Now, follow me? Keep going.
Sine pi of p.
What do you think?
No.
Based on the cosine? Probably not, no. Unless they have very limited values of P. But again, is it positive? Keep going.
4p times 1 minus p.
All right, enough of this. I mean, you get the idea, right? I have the solutions for this thing too. I'm sure that's right. I guarantee. Let me see the next one, because I'm trying to get through, what I'm trying to do is just make you aware of what he wants you to be aware of, and these problems are great at bringing that. Don't worry about 1-3, but it's a funny one. Zipf's law says the probability of the kth most popular word in English and other languages is proportional to 1 over k, where k is. So we'll talk about that one next time. It's a little long. What is this?
Spray, whiteboard spray.
No, keep it for now. I'm going to go upstairs and get, they have this spray bottle stuff that they use with Windex. I'm going to get that. Okay, look at 1-5. Now I'm going to show you something that's a little, for this problem, you'll understand what I'm doing. Have you had binomial distribution in Bernoulli? Have you had binomial distribution?
Bernoulli's? I've heard of Bernoulli's before.
No, have you had binomial distribution?
Is that the binomial theorem?
Yeah, but I mean, it's like, if you have n possibilities, how do you?
Yeah.
Probability of
Choose
thinking
K,
tail.
yeah, okay.
Okay, so this is something that binomial theorem applies here. We're not going to, I mean, Bernoulli process, I should have said that. I appreciate the whiteboard thing. I promise you next time I'll have some. Wait a second.
There's some spray over there.
I am. Blindness is a problem. I've had a lot of
problems with erasers. Matter of fact, the students last semester got an eraser for the classroom. Nick Stokes, is he here this summer too? No. He, I think, has that, but I'm gonna check over the facility. That's a good eraser. Which one? Were you in class last night? Do you remember that eraser?
Yeah.
Yeah, Blake. I'm gonna afterwards remind me when they go see if it's there. It makes a big deal. I mean, difference. I like to use a board. I do not like just PowerPoint. It's put people to sleep. When you get it, please get the book. I don't know if there's PDFs online or not, but please get the book as soon as possible. Didn't I put that in that OneNote thing? Put it in the syllabus? Can you check for me? Okay, next one. So you got a coin, or sorry, you better read it.
So, a fair coin is flipped.
Okay, this is a good one.
Let me read all of it.
Yeah, so you know, coin is either heads or tails. And it's fair means 50% chance of either. That's all he means by fair coin. Go ahead.
A fair coin is flipped until the head appears. Let the number of flips required be denoted by N. The head appears on the nth flip.
All right.
Assume the flips are independent. Let the outcomes be denoted by K for K equals 1, 2, 3, etc. The event N equals K.
Let me translate what he's saying. So first with a coin, if it's flipped, there are two possible outcomes, heads and tails. Those are the only possible outcomes. You can call heads 1, tails 0, it doesn't matter. Now, if you think about that, and it's a fair coin, if you toss it once, the probability of the head is going to be 1/2, the probability of the tail is 1/2. If I toss it, he wants the probability of on the kth toss, it gets a head, right? Is it conditional that before that it was just tails? That's what I want, and you'll see this. You see what's going on? Good. Doesn't he say that?
So that we're not saying that again.
Yeah, he's saying if you look at this, what is the probability a head occurs on the first, if you just toss a coin? It would be 1, right? Half. What is the probability of a head occurs on the second one, but not the first one?
1/2.
What would it be? Think about it. Let me get it this way. The 1 is a success. So you can have 0, 0 is 1, right? 0, 1, 1, 0, 1, 1, right? So the probability, this is the event space, all possible values or the set. With me? What is the probability of this occurring? It would be 1/4. Just look at the possibilities. You all follow me on that, class? That would be on the second one. What about the third one? In other words, 0, 0, 1.
1/3 or 1/8?
1/2 cubed, 1/8. You follow me on this? He's saying just on, the easiest way to do this, you'll see it on the third one. If that's what he's talking about, I think he is. All possibilities, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, right?
Where's the third outcome coming? The third.
Here's the first coin toss.
First coin.
Second coin toss.
Okay.
Third coin toss. I think that's where he's talking. The kth toss, you're going to see exactly what it, can you see it now?
Yeah.
How many see it? It's going to be 1 over, or 1/2 to the k power. You all follow me? Good. I hope. Do you see it? Or not?
You usually use a factorial.
Yeah, you can do it. We're going to, what you're doing is, you're using binomial coefficient stuff. But what you're doing is taking n factorial over k factorial, n minus k. Yeah, but that's, we are only worried about one value.
Yeah, okay.
He's looking at something further down. I know I'm about out of time.
I really wanted to go through some of these things and just talk about it, because when you see how straightforward it is, you can get lost in the shuffle if you don't see the simplicity of some of this stuff. So this is fair point is flipped until heads appear, so 1, 2. When the number of flips required be denoted N, the head appears in the nth flip. Some flips are independent, they happen. Let the outcomes be denoted K, we want to denote the event means exactly K flips are required. All right, we're not gonna have time. This is the binomial that I will talk about next time. I'm gonna ask you to do some, first read chapter 1 from Monday, and then I'm gonna give you a sense of problem here. Most of these problems you can fly through. There are going to be a few, like this length problem here. I showed you how to do this, but it's going to have different probabilities here, but I think you guys can handle it. Please do these things. And any questions you have? I mean, can y'all get a book by this weekend? Oh, sorry, I didn't do this. What I do, he's taking a video of this course, and I really appreciate it. And it will be posted, but I try to get people to do. Did you do a Facebook last time, or what kind of group me? What kind of page did you have?
I had a group me.
Can you guys do this time? I mean, both you guys, get a group me together, send me the link, I'll send it to the class. Now here's the deal. I don't know, you guys may come across a PDF of this. You may come across all sorts of information out there. As long as I ain't part of it, I can't get in trouble for it. All right, now that's where the group me comes in, and you can post these videos. I haven't had a lot of complaints about anything that happened on the chat or with these group me things. People seem to like them. I think the videos helped you. Blake, didn't you watch them several times in the last class, or not?
I made them and then.
I mean, but
Yeah.
somebody would respond and they'd go through them and tell me, and they'd come with questions about it. But I think they're helpful, so I'm going to do it. And does anybody have a PDF of this book? You got one? Can you put it up for me?
Yeah.
Thank you. Keep me out of it. I'm trying to help you guys. I feel for you, because this stuff it gets hairy very quick if you don't stay up with it, especially when you're confused about some point, like the series versus parallel stuff. That's usually a point of confusion. Okay. Did you all understand today?
Yeah.
I'll give you homework, and I'll give you solutions or answers to whatever I've got. Most of the stuff, to be frank about it, is not that hard right now, but it will get hard if you don't keep up with special condition probability. That's the stuff. You get into these distributions that are relative. You're laughing.